Hello everyone and welcome to Danesh Academy YouTube channel. Today we're diving into the interesting world of LiDAR sensors. In this video, we'll explore what LiDAR is, how it works, and its incredible applications across various industries. So let's start together and discover how LiDAR sensors actually work. Let's begin our journey by going back in time to learn about the interesting history of LiDAR sensors. Then we'll see how they work and understand the basic principles behind them. We'll also look at different types of LiDAR available. After that, we'll explore the many ways LiDAR is used in different areas. Finally, we'll discuss the benefits about LiDAR as well as its difficulties. So, let's start with the story of LiDAR. LiDAR, short for light detection and ranging, started with lasers in 1960. In 1962, scientists at Hughes Aircraft began developing it, and it became important during the Apollo 15 mission in 1971. Over time, with better lasers and computer programs, LiDAR became useful for mapping, surveying, and other jobs. By the early 2000s, with better lasers and faster computers, LiDAR became even more powerful. It became crucial in mapping, surveying, and monitoring the environment. Now, let's take a closer look at how LiDAR sensors are built. These sensors have a few important parts, each doing something different to help them work. First off, there's a laser projector. It sends out pulses of light to reflect off objects. Then, we've got the scanner. It moves the laser around to cover a big area and collects the light that reflects back. Inside the LiDAR system, there's a fancy electronic part that uses mirrors to move the laser beam. This part also has something called an inertial measurement unit, IMU, which helps keep track of the sensor's position and movement. The global positioning system, GPS, is another important feature giving precise location information. There's also a laser detector which catches the light reflecting back, and finally there's the control and data processing unit. This part manages everything and turns all the data into useful maps or pictures. So, all these parts work together in a LiDAR sensor to help us understand what's around us, whether it's for making maps, finding our way, or keeping an eye on the environment. Now, let's dive into the basic principle behind LiDAR sensors, calculating distance. Imagine a scenario where we have a transmitter, a receiver, and a reflector. The distance from the transmitter to the reflector represented as TL. To find the distance, we use a simple formula as follows. Here, C represents the speed of light. By multiplying the speed of light by the time it takes for the light pulse to travel from the transmitter to the reflector and back to the receiver, and then dividing it by 2, we can accurately calculate the distance between the LiDAR sensor and the object. This fundamental principle forms the basis of how LiDAR sensors measure distances in their surroundings, enabling them to create detailed three-dimensional maps and point clouds of the environment. On this slide, we'll explore the LiDAR scanning process through an animation. We have 3 videos to help us understand it better. On the left, you will see the scanning mechanism in action. This video illustrates how the LiDAR sensor moves to cover a wide area, ensuring comprehensive data collection. In the middle video, you will witness the laser's journey through a basic scene. Watch closely as the laser beam emitted by the LiDAR sensor interacts with the objects in its path, reflecting back valuable information. Finally, on the right, observe the sensor's output after the collected data is processed. The video showcases how the raw data, initially in polar coordinates, is converted into Cartesian coordinates, providing a clear representation of the environment. Together, these videos offer a detailed insight into the LiDAR scanning process, from data collection to final output, highlighting its crucial role in various applications such as mapping, navigation, and environmental monitoring. Now let's explore different types of LiDAR sensors. A LiDAR sensor is a specialized type of LiDAR system that relies on scattering to analyze atmospheric properties. Scattering occurs when particles in the atmosphere are similar in size to the wavelength of the light emitted by the LiDAR system. This sensor is primarily employed for studying aerosols, clouds, and other atmospheric particles. Mie scattering, named after the physicist Gustav Mie, describes the elastic scattering of electromagnetic radiation by particles of comparable size to the incident wavelength of light. Rayleigh LiDAR is another variant of LiDAR technology, utilizing Rayleigh scattering to investigate the atmosphere. Rayleigh scattering involves the elastic scattering of light by particles or molecules much smaller than the wavelength of the incident light. With Rayleigh LiDAR, laser pulses are emitted into the atmosphere, and the collected backscattered light provides valuable insights into atmospheric conditions. Raman LiDAR stands out as a specialized LiDAR system, leveraging Raman scattering to examine the composition and characteristics of the atmosphere. Raman scattering is an inelastic process where light interacts with molecules, causing a shift in the scattered light's wavelength. In Raman LiDAR, this wavelength shift offers critical information about the molecular composition of the atmosphere. Differential absorption LiDAR, DIAL, is a special way of using lasers to study gases in the air. It helps scientists measure how much of certain gases, like pollutants or greenhouse gases, are present in the atmosphere. This method is really good at detecting even tiny amounts of these gases with very high accuracy. In the picture, you will see some important parts of a dial system: the laser, which sends out the light, the photodetector, which collects the light that bounces back, the telescope for focusing, and the device that does the measurements. The image also shows how some of the light scatters back towards the laser, which is useful for the measurements. Now, let's talk about the online and offline wavelengths. These are like two special colors of light that the dial system uses. Each color is absorbed differently by different gases. The graph shows how much of the light is absorbed at these two colors. By comparing them, scientists can figure out how much of the target gas is in the air. So, dial helps us understand what's in our air and how much of it there is, which is really important for things like air quality and climate change research. Let's dive deeper into how LiDAR sensors are used in various ways. LiDAR is like a high-tech detective that helps us understand and interact with our world in amazing ways. LiDAR is essential for self-driving cars because it acts like their eyes, scanning the environment with lasers to create detailed three-dimensional maps. This helps the cars understand where they are and what's around them. Companies like Waymo and Cruise use LiDAR because it works well in different light conditions, including at night. These three-dimensional maps help self-driving cars navigate safely, avoiding obstacles and reacting to changes on the road in real time. LiDAR's ability to create accurate maps and work in various lighting situations makes it a crucial technology for the future of autonomous driving. It allows self-driving cars to see the world around them, making drivers safer and more efficient for everyone. In cities, urban planners rely on LiDAR to create incredibly detailed maps. These maps aren't just for looks. They are used to manage traffic flow, plan public space like parks, and even track changes in tree coverage over time. LiDAR helps make cities more livable and sustainable. Builders and construction crews also turn to LiDAR for precision. Before construction begins, LiDAR surveys the land to make sure buildings are placed correctly and that the ground is stable. During construction, LiDAR monitors progress and checks for any mistakes, ensuring that projects stay on schedule and on budget. Scientists use LiDAR in seismography. By analyzing how laser beams interact with the Earth's surface, researchers can track subtle changes over time, like shifts in tectonic plates or erosion patterns. This information is crucial for understanding natural disasters like earthquakes and landslides. On farms, LiDAR helps farmers make smarter decisions. By scanning fields from above, LiDAR can pinpoint areas that need more or less water, fertilizer, or pesticides. This not only boosts crop yields, but also minimizes environmental impact by reducing waste and runoff. The LiDAR sensor in the iPhone enhances camera performance and augmented reality features by measuring distance and depth with lasers. This improves object detection and distinction, especially in photography and augmented reality applications. Especially, it enables depth photography, enhances augmented reality experiences, improves autofocus accuracy, and facilitates depth detection for various applications. Overall, the LiDAR sensor boosts camera performance, object detection accuracy, and augmented reality efficiency on the iPhone. As we conclude, let's explore the benefits of LiDAR sensors. Firstly, LiDAR sensors provide exceptional precision, delivering highly accurate measurements, crucial for tasks requiring detailed spatial information. Another key advantage is their ability to generate detailed three-dimensional maps, facilitating better visualization and analysis of terrain, structures, and objects. LiDAR sensors excel in long-range detection, enabling the spotting of objects from afar, making them invaluable for applications like autonomous driving and environmental monitoring. Moreover, LiDAR sensors boast fast data acquisition capabilities, swiftly gathering vast amounts of data for real-time decision-making and rapid mapping. LiDAR's versatility shines through, finding applications across various industries, from agriculture to disaster management, offering flexibility and adaptability. In terms of safety, LiDAR sensors are highly effective in obstacle detection, enhancing safety in autonomous vehicles, drones, and robotics. Furthermore, LiDAR sensors demonstrate remarkable weather resistance, performing reliably in adverse conditions like rain or fog, ensuring accuracy in challenging environments. Lastly, while the initial investment may be significant, the long-term benefits of LiDAR technology, including improved efficiency and safety, often result in substantial cost savings and a solid return on investment. In our exploration of LiDAR sensors, it's essential to know some disadvantages. Firstly, they can be quite pricey, which might not be feasible for everyone. Secondly, LiDAR sensors are sensitive to changes in environmental conditions, such as varying light levels. Additionally, some types are big and heavy, which can make them hard to install and use. Moreover, regular maintenance and repairs can add up to significant costs over time. Lastly, certain LiDAR sensors may struggle to perform optimally in adverse weather conditions like rain or snow. It is better to know that Tesla doesn't use LiDAR sensors in their self-driving cars because they believe using cameras and smart computer programs is a better idea. These cameras take pictures of what's around the car, helping it understand things like where the lanes are and if there are any obstacles. This method is cheaper and can work in different driving situations. Because LiDAR sensors are expensive and struggle in bad weather, using cameras is a more practical choice. Perhaps Tesla wants to make self-driving cars available to more people and keeps improving their system to make it better and safer. Thank you for watching this video and exploring the fascinating world of LiDAR sensors with us. If you found this content informative and engaging, don't forget to subscribe to our channel for more insightful videos on emerging technologies and innovative applications. Feel free to leave a like and share your thoughts in the comments below. Until the next time, stay curious and keep exploring.